Assalamualaikum warahmatullahi taala wabarakatuh and salam sejahtera. Okay, today we're going to continue with the topic stated by our syllabus in the course informations. As shown here, we have alhamdulillah completed discussing issues regarding Ampere's circuital law. And now, based on the statement here, we need to continue to talk about introduction of the curl concept, Stokes Theorem, and magnetic flux density. Okay, they're going to be three major issues that I'm going to discuss in this video. Okay, with that, we're going to continue talking about curl and Stokes theorem. Yeah? Okay, so for those who have textbook, you can refer to page 85, where Sadiku discussed about curl and Stokes theorem in quite detail. For me, I'm not going to talk about the theory here. I'm going to straight away go into the application of this curl model in the field of a magnetostatic field. So therefore, that's my concern. The theoretical part, I leave for Sadiku to explain to you. So my main concern here, I'm going to talk about the application side of the curl model. Okay, so what we have now a scenario such that, let's say you have a magnetic field profile as shown here. So therefore, this red line is assumed to be our magnetic field intensity H. Okay, at a certain point on this particular space, I want to analyze the behavior of the field with regards to curl model. Okay, so for us, curl is just a mathematical model. So I want to analyze H based on the curl model. So you will see the significance of this model later on, but at this junction, we just need to know what is this topic all about. We just need to analyze this H at this point with this model. So therefore, this intention need to be defined mathematically with this equation. Okay, when I have curl, this should be my equation to represent the model. Okay, what field that we are dealing now? H. So therefore, this equation is known as curl of H. Okay, whenever you see this type of equation given to you, so this is known in terms of word as curl of H. Okay, I think you have seen this idea being proposed to you before in electrostatic, where we have seen a mathematical model known as divergence model, and then we call that model as divergent of D. But in this case, due to this equation shown as such, so this should name as curl of H. See how we proceed with this equation. So in order for us to solve this equation is very similar to the way you need to or you did in a solving problem based on divergence model, where you have to refer to equations. Since we have del notation here, we know that this notation is dependable on type of coordinate system. Therefore, logically now you're going to have equation based on various coordinate system. For Cartesian, if you are referring to Cartesian coordinate system, you have to refer to equation number 3.44, where on page 85 in our textbook. Okay, if somehow I want to use cylindrical as my preferred coordinate system, I have to use equation 3.45. Yeah? Finally, because we have three different coordinate systems, so we just need to label them for spherical coordinate system. The equation going to be, as you can guess, 3.46. All this equation available on page 85 in our textbook. Okay, that's how we go forward. Okay, whenever we see this curl model need to be solved, we have to go back to which equation that we are using in that problem solving. Then we have to refer to appropriate table as shown here. Okay, so that's what we need to know regarding curl in our concept here. Not the theory behind it, because the theory, I presume you have learned in engineering mathematics. For us, we want to use it here. Okay, so now, so what should be the solution for this curl of H be equal to? Okay, that's what our concern now. What actually the results of curl of H indicate to us? So with that, I'm going to go for example. Okay, so let's say you have a conductor. Okay, a conductor. Remember, this problem have been solved before, so meaning that nothing new. The radius of the conductor is what? Yes, as you can guess, A. What actually flow in the conductor? Good, I think most of you can already guess by now. There's a current, total, I. Okay, and then from previous example, okay, from previous examples, okay, we know that H, okay, 1, where this H1 indicate R smaller than A, okay, in the region R smaller than A, the field H equal to I R over 2 pi A squared in phi direction. That is our solution, and we also have determined for H region 2, where H region 2 is R greater than A equal to I divided with 2 pi R phi directions. Okay, now what we need to do, determine curl of H in both regions. Okay, that should be our question now. What should be the curl of H in both regions? Okay. Okay. Okay, so let's solve this problem now. Okay, the solution now. Okay, curl of H in terms of equation is equal to this formula, correct? So now the way we're going to solve this formula, as mentioned before, we must refer to appropriate table. And from this problem that we have solved before, which coordinate system that we are referring this problem to? Okay, and then we already know that the coordinate that we adopted to solve this problem is known as cylindrical coordinate system. So for you who have textbook, you can open to page 85, equation 3.45. So I'm going to refer to equation 3.45. So what does the equation give us? So please open the books if you have. It's quite lengthy for you to remember. I just copied the equation now from the textbook. 1 over r d hz over d phi minus d h phi over dz in which direction? Yes, r directions plus. Okay, just copy the equation. Inshallah, the equation will be given to you in tests as well as in your final exam. So you don't have to memorize the equation, just need to know how to use it. Okay, minus dHz over dr in phi directions. Okay, and finally we're going to have plus 1 over r open bracket d r h phi over dr minus dhr over d phi in z directions. Okay, that should be the equation referred to the table. Nothing extraordinary, just refer to the appropriate table. Okay, now what we have to do now, we need to solve the problem. Okay, for region 1, okay, what does I mean by that? What should be the curl of H1 equal to? Okay, so what we have to do now, we have to see in our equation H1 given here. Okay, so what component of magnitude that given in this particular H1? So given here is only consists of H component of phi, correct? So therefore what we're going to state now, H component of R is equal to H component of Z is equal to what? Yes, good, 0, because that's term not available in our original H1. In H1 only contain the magnitude of the phi component. So therefore we need to assume the R component of H as well as the Z component of H will be equal to 0. So what you need to do, we have to refer to the equations and then we need to substitute everything in the equation. Okay, let's see. This first term, Hz, should be equal to what? 0, correct? The phi term, okay, what we need to substitute with? Yes, we need to substitute with I r over 2 pi a squared. Remember, we need to ignore the direction, just substitute the magnitude only. And then here, what should be the HR term? Good, 0. Hz term, 0. Okay, this particular side of the equation, H phi term here, yes, you need to again substitute with IR over 2 pi a squared. And then for the HR at the end of this equation will be equal to 0. Why? HR 0. So therefore we already end with this substitution equations. Then we need to solve the mathematics. So if I solve the mathematics based on the R term here, okay, the Z is 0, but the H phi here consists of this equation, but yet we have to differentiate with which term? The Z term. So therefore, if I differentiate with the Z term, what will be the solution of this differentiation? Good, 0. So I'm going to have 0 R component, because 0 minus 0. This way, 0 R component of the mathematics. So I'm going to have 0 Z, phi component, correct? Because 0 minus 0, phi component, so end with 0. And the last term, which is the phi, I have to substitute carefully now. okay, d over dr. Now I'm going to have 1 over r. Remember, don't forget 1 over r in front here. Okay, and then what I need to differentiate here, ir square over what? 2 pi a square, correct? Then after substitution and multiplying with the r, okay, ir over 2 pi a squared, you need to multiply with the r, becoming ir squared 2 pi a squared, and then the second part of the z term will be equal to 0, so therefore z. So if I solve the mathematics now, I'm going to end with the z term only. Okay, here 2 ir squared, so 2 ir. Okay, I'm going to have here 1 over r. Okay, 2 ir divided with what? 2 pi a squared in which directions? Z directions. And then it's going to be equal to what here? Equal to I over pi a squared in Z directions. Okay, that should be the solution of the curl model for region number 1. So what does the meaning of this solution? That's what we need to address now. What does it mean to us? Okay, so let's go back to our problem. So if I ask you to find what should be the J here, okay? So determine J. J is current density, remember? Okay, and then the way we define the J inside this conductor is defined as total current, remember? Total current divided with what? Total area. And then the current flow upward, we already defined it to be positive Z. So what should be our total current? Yes, total current given by the problem is I. What should be the total area? Pi a squared. So now let's compare the J that we define based on the problem and our numerical solution that we obtain based on the curl model. So what we can see now, they are the same, correct? They are the same. This current and this current are the same. Okay, so therefore what we can state now, this actually equal to J, volume current density. Okay, so meaning the curl of H actually can be defined to be equal to the source of the field, the J. Okay, so therefore we can state that as one conclusions. Okay, maybe some of you still not feel convinced, so let's prove based on our second region now. So for region number 2 now. Okay, so what should be your curl of H2 equal to? Okay, you need to do the same process as before, as in curl 1. Okay, what should be the curl of H2? Okay, you just need to substitute everything, but now what you need to substitute is I over 2 pi r. Okay, I'm just going to focus on the second term here, sorry, the Z term here, what I'm going to have 1 over r, okay, d over dr, and then what I'm going to have now is r I over 2 pi r, correct? And then that should be the Z directions. I just substitute I over 2 pi r. So now what we can see based on this substitution, we're going to cancel the r, correct? So when you cancel the r, the term now becoming constant. So therefore, if we differentiate something constant, the end result will be equal to 0. So then we ask ourselves, if there's any current actually exists in region number 2, there's no current in region number 2, correct? So therefore, this also can be defined equal to J. J that actually appearing in region number 2. There's no current in region number 2, therefore the current density in region number 2 is equal to 0. Therefore, by doing the curl model of H2, we're going to confirm even though the field does appear in that region, yet there is no charge or no current exists in that region. Okay, so with that, we have conclude now the outcome of curl model. Okay, so what we are conclude now, okay, the curl model, okay, the curl of H here is equal to J. Okay, that should be important equations, and this equation, as what you can guess, Maxwell equation number 3. Then if you compare to what we have seen before, divergence of D equal to rho V. This is known as Maxwell equation number 1. Okay, so by now you can see clearly whatever we have done in the world of electrostatic, the same flow or the same concept reappear in the world of magnetostatic. So the idea been discussed before based on divergence model in the world of electrostatic. So the same idea been discussed again, but slightly different model. Here we are using curl model, but yet the final conclusion that we deduce from both method are the same. They are proposing what known as Maxwell equation, Maxwell equation number 1, as well as Maxwell equation number 3. Okay, so let's go further now after introducing Maxwell equation number 3. So I'm going to talk about Stokes theorem now. Stokes theorem. So Stokes theorem. Okay, from Ampere's circuit law, we know that H dot dl is equal to I enclosed. Okay, and for the general case of current source, we assume the current is known as volume current. And for volume current, we can define it to be in more detail as current density dot with ds, the standard equation that we use to relate to volume current source. So just now, we have been introduced that this J can be substituted with Maxwell equation number 3, where curl of H will be equal to J. Remember that equation that we proved together using the curl model mathematics? Okay. Now, what we can conclude for this equation, the right-hand side equation can be n with the integrations, curl of H dot with ds. So what we can see from this equation is that if you want to convert mathematical equation based on surface integration, line integration to become surface integration, we just need to use this equation. Okay, this equation will help us to convert any equation that defined in terms of line integration to be in surface integration. We have to use this equation, and from the name of this discussion, this equation is known as Stokes theorem. Or in other words, Stokes theorem is the theorem that we use to convert mathematics from line integration to surface integration. I'm sure you have seen this idea being proposed to you before. It's known as divergent theorem. Remember divergent theorem? Okay, in divergent theorem, what we state is that d dot ds will be equal to divergence of d dv. Here, mathematically, you can convert from surface integration to volume integrations. Okay, so now if I want to convert my mathematics from surface to volume, what I need to do is that first I need to use Stokes Theorem. I change my line model mathematics to become surface model mathematics. Then from there, I'm going to adopt divergence theorem, where I can convert my surface integration to be volume integration model. So you can do that mathematically. So that's by adopting Stokes theorem and divergence theorem. Okay, that's what we need to know about Stokes theorem. Just tools that you can use to convert certain format of mathematics to other format, yeah? To be more specific, from line integration to surface integration. Okay, so now I'm going to continue. So the third issue that we need to discuss is known as magnetic field density. Magnetic field density. That should be our next concern. Magnetic field density. And the symbol that we're going to represent magnetic field density is known as vector B. Okay, that should be our objective here. But I'm going to make it slightly different now. I'm going to reuse our experience in the world of electrostatic. Okay, because again, I'm stating something that obvious. What you learn in electrostatic is going to be repeated again in magnetostatic. So why not we use our experience before in this current discussion, just to confirm with our belief that they are interrelated. So let's talk about electric field density. So the difference between these two types of field, you can see they are having different color representation. So now, electric field intensity, we give it as symbol D. Okay, so assume the medium free space. Assume medium free space for both cases. Okay, for both cases, so free space as well here. So I can say to myself, this symbol is known as what? Anyone can recall the name of this symbol? Good. Electric field, electric flux. Okay, that symbol to for this, the name for this symbol. So in the world of magnetic field, we are using the same symbol, but different subscript. So this is known as magnetic flux. So then I already know the way I'm going to relate the electric flux to electric field density by stating that electric flux is equal to the integration of what? D dot ds. Okay, that's how we relate between electric flux density or electric field density to electric flux. Similarly, I can use the equation to relate my electric flux with my electric field density, B dot ds. Okay, you can use that equation to determine magnetic flux. Okay, so you can see whatever we experience in electrostatic can be used again in magnetostatic. Okay, so let's go on now. So then we've been introduced E. So what is E? Or vector E. So E is our electric field intensity, correct? Okay. And now we already know that the similar component that we can have in the world of magnetostatic is H. And H here known as magnetic field intensity. Okay, why? Because we can relate D and E by D equal to epsilon naught E. Okay, because we are still in the medium of free space. And this epsilon naught is known as permittivity of free space. Permittivity of free space. Similarly, if I want to relate H to B, I can say that B is equal to, okay, now we have used different parameter, mu naught H. Okay, mu naught here is known as permeability of free space. Okay, so permeability, whereby in the world of electrostatic we call the parameter known as permittivity. So that's the main difference now between magnetic domain and electric domain. The constant representing the material now going to change slightly. Okay, so let's continue. The last equation that we're going to discuss. Let's see if I going to do this problem solving. Let's say I do this mathematic d dot ds. What will be the solution it's equal to? Okay, and all of you will gladly say the solution to this particular mathematic will be equal to Q enclosed. Why? Because this is known as Gauss law. Okay, therefore, what will be the solution for, I'm going to copy now. Let's say I'm copying now. D and changing into B dot ds. Okay, the solution now not the same anymore. This is going to be equal to 0. So therefore, please remember they are not equal. They are different now. So this equation is also known as Gauss law, but in magnetic field. Gauss law in magnetic field. Okay, so I'm going to conclude my discussion now with this final equation. For point form Gauss law, of Gauss law, what should be our equation? Good. Divergence of D equal to rho V. Okay. Now what we have now, the point form of this equation will be equal to what? Divergence of B, okay, will be equal to, as stated here, is what now? 0. Okay, for your information, this equation that we are discussing now is known as Maxwell Equations. Number what now? Yes, number 4. Okay, so therefore we have seen all the Maxwell equations need to know in this particular subject, which are 4 to be specific, 2 from electrostatic and 2 from magnetostatic. So let's summarize that in our final discussion here. I'm going to discuss now Maxwell equations. Why it's important? Because this is going to be our linkage to our world of electromagnetic later on. Yeah? So Maxwell equations. Okay, so I'm going to first define for electrostatic. Okay, I'm going to then we're going to talk about magnetostatic. So how many format that we can represent our Maxwell equation? We can call in integral form, and also can be represented in point form. Okay, that should be okay. So now I'm going to divide further into 2 into 2. Okay, so let's recall the first Maxwell equation. We call it Maxwell equation number 1. We d dot ds is equal to Q enclosed. In other words, we also know that as Gauss law. In point form, we have proved this equation together when we talk about the divergence model, okay, equal to rho v. Okay, and the second Maxwell equations that we observe when we talk about potentials, and then we said that E dot dl is equal to 0. Okay, that should be our two Maxwell equations that we have seen in the world of electrostatic. In the world of magnetostatic, black in color, so we know Ampere's second law given as H dot dl equal to I enclosed, correct? And then we just proved in this video that the curl of H is equal to J. Okay, by comparing our equation number 2 and equation number 3, since they have the same pattern here, I'm going to conclude the point form can also be the same. Okay, therefore, for point form of equation number 2, can be stated that the curl of E here will be equal to 0. And finally, in our recent discussion, we are saying that Gauss law in magnetic field, B dot ds is equal to 0, and using the same pattern that we observe for equation number 1, therefore we can state now divergence of B will be equal to 0. Okay, why this topic is important? Because what we want to do later on in this syllabus, okay, we're going to talk about the field known as electromagnetic field. Okay, so this is going to be our electromagnetic field. Okay, this is going to be our objective, final objective. So the way for us to migrate from static, okay, static to time varying by utilizing Maxwell equation. What you mean by that? All these equations going to be recalled again when we discuss about electromagnetic. Okay, in other words, Maxwell equation are the bridge linking the world of electromagnetic and what you have learned before. So all the issue that you learn in electrostatic still relevant in the world of electromagnetic, but with the utilization of Maxwell equation. So please remember, this equation is important because this bringing this bridging, linking the gap, linking the three different fields that you going to learn and you have learned. Therefore, as I mentioned in EMT, it's important to understand what you are learning now, because that understanding will affect your future understanding in the world of electromagnetic. Okay, so therefore I'm going to talk about this equation in more detail when we start discussing about electromagnetic. So with that, Alhamdulillah, we have completed our task stated by the syllabus in the course information. Thank you for your attention, and inshallah we're going to see again in our coming video. Assalamu alaikum warahmatullahi wabarakatuh.